I figured in this brief time, since I'm new to the campus, I would just briefly say a little bit about myself. I just recently moved here from the University of Manitoba, where I spent 19 years post PhD. At the University of Manitoba, I basically ran a lab which we call the Collaborative Visual Analytics Lab. A lot of emulation hardware, emulation in virtual reality of future user interfaces, some of that equipment is actually over here, so we are quite fortunate to have had some of the equipment come with us. So this was a group that we had over there, and still I haven't transferred my website to UBCO, but that's in the works. I'm also still running a Enter Create program on visual and automated disease analytics, and more information can be found at that website. For students who may be interested, we have extended it now it's a program between the U of M and the University of Victoria, but since I moved here, we've also extended to including students from UBC. Okay, in terms of my work, so I've been, my background is in data visualization, and I've been primarily interested in looking at the idea that in the information age, where much of the data guides how we behave and how we act and what we do, has largely been at the disposal of a few elite people, typically considered to be data scientists. And my work has been primarily looking at how can we actually take the tools, the power that data scientists have, and give them to the masses. That is, if we are going to become data literate in the future, generally speaking, we need end users at large to have access to this data, to be able to slice and dice through it, and to be able to make sense. The data pyramid that's very commonly presented is where you start with some raw information or raw data, you move it in processing into information, knowledge, and ultimately wisdom, is typically what we are trying to achieve in our work. And of course, there have been lots of initiatives, the Open Data Initiative, the Data Literacy Initiatives, and the Visual Literacy Initiatives, which I won't talk about here, but certainly these are some very important facets, looking at visual literacy from a very early age. What does it mean to give young kids ability to understand visual information of data, of graphs? How do they become more savvy and more cognizant of, for instance, financial questions or personal health questions or biometrics? Now, if you think about data that is available to the masses, there's a whole range of them. We have data about our financial situation, data about our work day, and we also have, generally speaking, the consumer public, we have a lot of data about our biometrics, that is how we are doing on a well-being perspective. And more is being collected through sensors that you have worn by users. So we are generating massive amounts of data through these sensors. And the question remains as to how do you actually, go about navigating these large information spaces. So we started asking, well, what is the kind of information users require? Because with many of these devices, you're given the information that the manufacturer wants you to look at. And secondly, how should this information be presented? So we actually have a few students working under this realm. You have a whole range of displays that are provided in terms of, what's your hydration levels, your step counts, and these are very static types of information. We are quite interested in moving beyond that and looking at the kinds of complex queries people may do. So for instance, we find out that users may want to ask such a question as, why is it that on my typical hike that is usually about, 5 to 7 kilometer hike, why is it that today, for some reason, I can't actually go beyond half of this hike? And ideally, you want your system or your watch perhaps to respond and tell you that, well, you perhaps didn't have a very good sleep over the last few days and your hydration levels might be low, right? And so these kinds of complex queries are not quite accessible, and this is generally the direction that we're taking on one front. So we see that the queries that people have about their data are far beyond what we typically have available to them. So we went into some of this exercise, and it's sort of talking a little bit more about our methodology in terms of the fact that we use both quantitative approaches, but also qualitative approaches. So where we seek input from graphic designers who produce the visual designs, we cluster and classify them, and then identify ways of augmenting the kinds of displays that we typically may have on these types of devices that people wear. Of course, presenting the information is one piece. We need to also interact with the information, and the question here remains as to how do you go about interacting with this information on the go. So here we've designed a number of techniques with students, bezel glide, page flip, looking at layers of information, just as you would peel layers of an onion. Looking at the idea of augmenting a device with sort of ultrasonic sensors to be able to detect gestures in midair, to be able to access the vast array of information, which you're getting through a very minimal portal. But of course, a lot of these require two hands. So in our lab, we look at also alternative ways of interacting with these systems that are convenient to users. So this goes and speaks to the first speaker, Dr. Leong's talk about human-centered design, where we look at from a human's perspective, what would be ideal in terms of, or what would be preferable. So here's an example demo of a prototype that kind of speaks to this a little bit.
In this video, we introduce a new input style using the wrist as a joystick to perform common touchscreen gestures to interact with a smartwatch using the same hand wearing the watch. We explore using the wrist for continuous input as a potential solution for these problems. We build our prototype smartwatch using a 2-inch display and a plastic watch strap augmented with 12 infrared proximity sensors and a piezo vibration sensor connected to an Arduino Do. The user can wear this device to draw common gestures by moving the wrist.
So I think you get the idea here. And so, our prototypes are very crude on the hardware front. They're probably quite minimalistic. We come mostly from the software side of things, where we try to embed, software in these types of low power systems and use them. And this is where we need to do more interdisciplinary work with engineers who can actually help us build, improve prototypes and improve devices. So if you look at this kind of sort of this type of data that surrounds users today, we can observe several things. One is that it generally supports some form of an activity. Maybe your physical activity, maybe you're trying to look at your well-being and your health, perhaps understand better your mood patterns over the last few days. And as these sensors become more complex, we get to actually understand a little bit more about ourselves and how we can navigate through the world. Generally, this information is being used on the go. So generally, as you're on the move, it needs to be interactive because you need to be able to extract information. You don't want to be limited to only whatever information manufacturers provide you. And oftentimes it depends on the heavy amount of visual feedback, allowing the user to navigate through it. But if you look at this type of information access and the idea that information can actually support activities, you actually see this occur in many, many instances. For instance, putting furniture together, you have the need for information that can guide you through that activity. Firefighters may actually use some kind of information and data to be able to move through mitigating wildfires. And also farmers, and the applications are numerous. So for instance, cooking through a recipe is a classic example that we use. And so we define this kind of computing as in-situ computing. So I apologize for bringing the definition of my title this late into my talk, but these are systems that support users in the context of a real-world activity. And the premise here is that current tools and devices are actually not quite suited to facilitate this type of computing. In our lab, we actually believe this is the next sort of paradigm in computing. So we have personal computing that has moved on to mobile computing, ubiquitous computing, and we are now looking at areas of in-situ computing, that is computing in place, embedded in the user's environment, and to support a number of different real-world activities, as the examples I illustrated earlier. So some of our questions lately, and this has been the question around my current NSERC Discovery Grant, is how do we actually design in-situ sense-making and user interfaces? So the idea that we want to be able to extract value out of that information in place and time to facilitate whatever you may do. So sense-making is basically a process of acquiring knowledge to make a decision. We actually distinguish between passive and active sense-making, and I won't talk a lot about our work on passive sense-making, but we're doing a number of works there that I can discuss at some point later. So the idea behind active sense-making is that you are navigating through pieces of information, and like I said earlier, that information ideally is necessary for the kinds of tasks that you may be doing on a daily basis. In terms of platform, we find that current platforms such as tablets, smartwatches, and the others are actually not quite suitable. They're very limited in their display size, whereas current emerging platforms such as wearable displays, wearable headset displays, provide you information that's always available. They actually have a potentially very large display canvas. Even though they have a very small field of view, their canvas is actually can be entirely your entire world. And the nice thing about this is that they generally allow your hand to be available to interact with the data, which can be useful because oftentimes your hand may be actually busy with the task that you're doing. So some of the questions we look at is how do we lay out such information? And here's an example prototypes of what we built and students have built in the past. So this is a personal facade. This is one, and you notice that this is, this is through an Epson display. So it's a very small window that you see over here. This was done before some of the devices that you have on the market today. And we had to actually build a lot of the systems underneath to be able to intelligently place the content in the environment without having to occlude the objects in the space. So here you have, for instance, the users extending their environment through that space. We also have something referred to as spatial constancy. So if you have certain windows, like your calendar on the right-hand side, regardless of where you go, the algorithm will try to find some optimal place to insert that information. And so we kind of tend to do this by extracting the surfaces of the model from the environment and using those models to embed into our layout generator, apply some heuristics for spatial constancy and for visual saliency. So the idea of being able to avoid information. So that's the kind of work we're interested in. Now this work came about 10 years ago, but it's nice. I always like to show the timeline. The Google Glass that I showed earlier was in 2014. We were using the Epson glasses way back in 2010. Actually, Epson Research Lab had a lab in Canada, in Toronto. I think it still does. And we were given a few glasses by them. The Google Glass came later. The HoloLens in 2016 actually has now some of the capabilities we actually showed way back then, and of course the Oculus Rift now more recently. Apple Glass actually now has a patent on some of the very similar ideas we are exhibiting in 2010, 2012. In terms of a display, that's one area that we are quite heavily involved in. The other area we're interested in is the interaction. And generally speaking, with such information that's generally your canvas, which is your all around the user space in the entire world, you're generally using mid-air input. That is, your hand is in mid-air trying to interact with the content. And this actually turns out to be okay, but it's not really ideal. So we actually designed some models to identify what's referred to as human fatigue. We actually have this metric called consumed endurance. And so we are also very interested in designing metrics in our lab. So consumed endurance is a metric for hand fatigue. But one of the other metrics we're designing now for these environments is for motion sickness. So I'll just quickly go through this video.
Mid-air interfaces facilitate natural user interactions as users freely move their arms in space to interact with the computing system. However, a frequent complaint among users of such systems is the feeling of heaviness and tiredness of the arm, a condition colloquially termed as the gorilla arm effect. To obtain an objective measure of effort for mid-air interactions, we propose a new metric called consumed endurance. Consumed endurance is the ratio between the time used for the interaction and the available endurance time, a measure derived from the biomechanical structure of the arm.
So anyway, we go through this, and it ideally actually helps us give us some fairly interesting guidelines in terms of how to lay out content and how to interact with content. So as you can expect, having content directly at shoulder level is perhaps not the best. And obviously that which is lower to the body and closer to the body is ideal. So we've actually used that information to build a whole host of devices. Figure 3 here was actually a device we built with a company, and they've considered it into their sort of headset product. The one on the right-hand side here is the Google Soli device, which is a different type of interaction through midair where you can actually attach it to your belt. And so we go through an iteration of these types of devices to ideally find the best user experience to our ability, and then to be able to embed them through engineering of those devices and integrating them into either existing or new products. And so you can think about, the idea of taking these types of metrics further, where you have mid-air input and then moving it further to the closer to the body, such as on the hand. We had doing some recent work on body hand user interfaces. So you have interfaces that basically, instead of having them hang in mid-air, you have them attached to your hand, and they can actually float with your hand. And so again, this is with an older device. But then you can move into, with some of the newer devices, you can do some fairly interesting use some fairly interesting types of algorithms where you can actually use deformable points along a surface that's changing and be able to modify the geometry so that it actually respects the deformation of the hand to give you that naturalness of interacting with the surface that's actually on your embedded or imprinted on your body. And so this is the outcome. This is through an Oculus Quest, for instance, where you can actually have that interface now attached to your head. So that's in a nutshell, very quickly, 15 minutes. The kind of work we are trying to accomplish is where we're trying to give improved user interfaces and user experience to be able to access a vast array of information. We are trying to move in situ kind of computing to general purposes from just specialized experiences. Of course, current platforms do not support in situ computing, so there's a fair amount of work there, and we are always interested in collaborating with members of the in engineering, in the natural sciences, psychology, and others to be able to continue building these interfaces. And so we realize that, of course, new interfaces are constantly being required to facilitate these interactions as they sort of emerge in our space. So I'd like to, of course, thank all the students who, these are just a sample of them, but many of the students who worked on our projects, which of course wouldn't have been possible without them, and many of our funding partners. I'd also like to thank the MMRI for inviting me here today and for presenting.